Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. To close out 2018 and open the new year, we're excited to present to you our first ever AI Rewind series. In this series, I interview friends of the show for their perspectives on the key developments of 2018, as well as a look ahead at the year to come. We'll cover a few key categories this year, namely computer vision, natural language processing, deep learning, machine learning, and reinforcement learning. Of course, we realize that there are many more possible categories than these, that there's a ton of overlap between these topics, and that no single interview could hope to cover everything important in any of these areas. Nonetheless, we're pleased to present these talks and invite you to share your own perspectives by commenting on the series page at twimlai.com/rewind18. In this episode of our AI Rewind series, we're back with Anima Anandkumar, Bren Professor at Caltech, and now Director of Machine Learning Research at NVIDIA, to discuss her take on trends in the broader machine learning field in 2018 and beyond. In our conversation, we cover not only technical breakthroughs in the field, but also those around inclusivity and diversity. Enjoy. All right, everyone, I am on the line with Anima Anandkumar. Anima is the Bren Professor at Caltech in the CMS department, and as of a couple of months ago, the Director of Machine Learning Research at NVIDIA. As well as being a good friend of the show, you can hear her previous conversation at TWiML Talk 142. Anima, welcome back to This Week in Machine Learning and AI.
Thanks a lot, Sam. It's great to be back. The past few months have been so exciting and so happy to see you do this show reviewing the year.
It is going to be a fun conversation, I am sure. Before we get too far in, maybe you can kind of share a little bit about what you're up to at NVIDIA.
Yeah, it's been an exciting couple of months at NVIDIA as we have released so many new frameworks and we have many new researchers and engineers and others join us. And my role is Director of Machine Learning Research there. And that means I want to focus on core algorithmic problems. How do we optimize neural networks in a principled way or generalize, think about reinforcement learning, generative modeling. So a broad class of machine learning questions, but focusing on the core algorithms, analyzing them, running careful scientific studies, and at the same time connecting with all the really interesting applications that we are seeing today.
So we're also speaking right on the tail end of NeurIPS, NeurIPS being a new name for the Neural Information Processing Systems Conference, a new name which you helped initiate. Maybe can you share a little bit about your experience at NeurIPS this year, as well as your thoughts on the name change?
Yes, Sam. I'm so happy to see NeurIPS take important stance on diversity and inclusion. In addition to having technical advancements, this is so critical because I feel like we are at this cusp where we can either, have a democratization of AI and have diversity and creativity from all the groups coming in, or we could have it closed off to only a certain kind of individuals, right? And the latter would be a sad thing, for the world and for AI. And so I'm happy this year that there was so much focus, not only on diversity and inclusion, but also on societal impacts, AI fairness, ethics, and we have people coming from those expertise, with those expertise into the conference. And that just makes it such an amazing place. I think it's changed for the better. There is so much awareness now about the issues affecting the underrepresented communities, and more allies coming to these diversity events, right? It's not an event that's only for those groups, but it's more of understanding the issues those groups face, and how the rest of the community can help bring in people from diverse backgrounds. And to me, the name change, the whole experience was part of this push for diversity and inclusion. When we saw last year, there was many issues where the name was used as a way to make fun and have jokes that bordered on sexual harassment. That is a problem. And to me, yes, some people may argue, oh, it's just a name or it's just a joke, right? But there are deeper issues that this name change helped us explore. I mean, I was personally very surprised at the amount of trolling I received when I spoke up about it. And that's why so many women cannot speak up about it, because they feel threatened. And so there are broader issues of how do we make this a safe and an inclusive environment for everybody. And I'm so happy that there are so many male allies, who strive to understand the issues better. They kept asking me throughout this conference, how do we make this better for everybody? What can I do? How do I help? Right. And that's why this has been just a unique experience. I have never experienced a conference like this before.
Yeah, it was a really amazing conference for me as well, on a couple of levels. First, I think there's been kind of a blooming of these different interest groups at the conference. So women in machine learning has been around for quite some time, and is kind of met in conjunction with the conference. But last year, for the first time, I attended the Black in AI workshop, which was the first time for that workshop, the second time this year. This year, there was added Latinx in AI, as well as several others.
I would add queer in AI. And, that's there was also the town hall on diversity and inclusion, where all these groups came together and discussed how there were unique problems for each groups, but also common ones, right? And then there is the whole issue of intersectionality, that a person may not just belong to one group, but several groups. And how do we think about these issues? And for a technical community, so much of this is new, and we are having experts from other areas, really educate us on these issues.
Yeah, what I thought was really interesting was the way, at least in the Black in AI workshop, both the technical issues as well as these intersectionality issues were all kind of weaved together. I don't know, it just, as an African American in technology, I'm often the only person in the room, for much of my career. And to, be in a room where, there are so many not only African Americans, but, Africans and Black folks from all over the world talking about cutting edge machine learning and AI, as well as the broader issues, surrounding not just our communities, but other communities. I left really inspired. And then beyond that, to see in the broader NeurIPS conference, the extent to which, some of these issues like not just diversity and inclusion, but fairness, accountability, transparency, they really took a kind of a top line, played a top line role, I think, in this year's conference, unlike last year, or I didn't notice it to that extent last year. So it was very, very, very nice to see.
I agree. Yes. And, I've been meeting lawyers, policy makers, people with expertise in ethics. And, you couldn't imagine NeurIPS having these kind of people, attend a few years ago. And that's, I think, great for the field.
So that was certainly an important development for 2018. And so maybe we can use that as a jumping off point to talk about some of the things on the research side that you are most caught your interest in the past year.
Right, Sam. There has been a lot of developments, so I'll just pick a few. Doesn't mean that, that the others are not important. There is just so vast, right? And that's what's exciting to be an AI researcher today, because we have so many domains and so many new kind of perspectives coming into AI. So some of the highlights personally for me, one paper I would pick is this video to video synthesis that appeared here at NeurIPS with a group of NVIDIA researchers. And what's really novel here is how to take this idea of image to image synthesis to videos, right? So over the past few years, synthesizing images through Gans has been very popular. And then the next step was, if you already have an image, can you transform it in a certain way to output another image, right? Like the idea of cycle Gans and other frameworks to do that well. But when you think about the videos, this is much more challenging because you have to maintain temporal coherence and you have to generate it for that whole length of time in a nice, smooth manner. And so there were many new advances in this paper. The main one I would call out is the spatiotemporal adversarial objective. So it's not just the space, it's not just the time, but the two have to come together. And this achieves good quality synthesis as well as coherence. So you need to think of these multiple objectives being achieved here. And they show that it's possible to generate 2K resolution videos of street scenes up to 30 seconds long using only the input semantic segmentation maps. And these segmentation maps were obtained from a renderer. Right. So the idea is now you can think that, you only get very quick, simple inputs from a renderer, and then you can actually use the GAN or learned frameworks to generate the output videos well. And so there's a lot of promise in this area. Videos are always much harder than images in so many ways, and I'm happy to see this development.
So in their approach, did they use, it sounded like you're saying they used just multiple objectives as opposed to a second adversary or critic? Were they like doing adversarial in multiple dimensions, time and space, or did they somehow combine those two objectives with the same adversary?
It was a single adversary, but it's spatio-temporal objective, so you combine both of them together.
You mentioned something about a renderer. Can you elaborate on that?
So in this case, the renderer was used only to get the semantic segmentation maps, right? Like, what is the area of the pixels that has the car? What is the area of the pixel that has the background? Right. And then the whole filling in was done using the GAN framework. And you could think in future, you could have like a mix of renderer doing some of the rendering task and then GAN helping it and kind of having combined free system.
Yeah, there's been so much interesting work happening that happened in the GAN space this year. I remember another one that was really interesting was the photorealistic images. I think also from NVIDIA researchers that really pushed the bar very far for what these generated images could look like.
That's right. There have been progressive GANs. There has been the big GAN paper, right? Like, how do we really push to very high resolution and ultra realistic images? And I think these are exciting developments in applied deep learning and can be applied in a lot of interesting areas.
Do you see GANs being applied beyond the image domain to other types of information?
I think, the idea of having a competitive optimization, right? At the core of it, there is the generator and discriminator, but you could think of other kinds of competition that's applicable in so many problems. I mean, if you want robustness, you now have this competition. If you have multi-agent systems, this framework would be applicable. So I would say at the core algorithmic side, yes, there are a lot of connections.
So video to video synthesis, what else has caught your eye this year?
Yeah. So on more the theoretical front, I will talk about some of the works we've been doing, looking from a different perspective, right? So I just said I've been excited about Gans, and Gans are great for now generating these photorealistic images. But what about applications where it's not good, right? So what are applications where GAN is not that easy to use? And that's for semi-supervised learning and other frameworks where you need to use the generative process to help a supervised task. And in this case, these are two separate systems. The GAN is separate from your convolutional neural network, which does the prediction, and it's very messy to try to combine both of them. Instead, we came up with a framework called Neural Rendering Model that tries to build a generative process right into your convolutional network rather than having a separate system. And its goal is not to generate good-looking images, but to ask what are the relevant hidden variables and what is the relevant variability I need to capture in the data into this convolutional network such that I can do semi-supervised learning well, and I can also regularize my supervised learning in a nice way. So intuitively, what it's doing is it's taking this convolutional network, which is a feed-forward system, and tries to reverse it. But then there is information loss when you're going through this network, so you're not able to perfectly reverse the system. Instead, what it's doing is it's saying, what is this uncertainty in reversing the process? Can I capture that well? Can I capture it across all the scales? And that gives me a measure of variability and uncertainty of each image. And we get state-of-the-art results, semi-supervised learning in this case.
What are the evaluation criteria, or what are the experiments that you're running, and what are you comparing it to?
Yes, in semi-supervised learning, the task is you have both labeled and unlabeled data, right? And you can do that with benchmarks like CFAR, ImageNet. There are a few other data sets. And the key is you have very little amount of labeled data and a lot of unlabeled samples. Can you still get good accuracy? And that's why this is a much harder task.
On a classifier.
That's correct. Right. On the held out test set. Right. Where you have to go and label that, but you only have few labeled examples in your training data set.
Mm-hmm. How does the performance compare between supervised and semi-supervised? How much of the gap have we been able to make up for not having the labeled training data?
I would say this is still very much an unsolved problem. The gap is significant. Especially when you think of ImageNet scale or on a large number of categories, mm-hmm. right? And I think that's why a lot of new works will be looking into this. Ultimately, in many other domains, we cannot have so many labeled examples. And how do we use all the unlabeled data to help this supervised task? I would say this is a hard problem to tackle.
Mm-hmm. And so this kind of reverse pass that you're describing that is trying to capture the variability in these images, how does that variability lead to performance on the forward pass side?
So I would say a primary challenge in machine learning is capturing uncertainty well, right? So if you look at the softmax at the very end of these convolutional networks, they don't do a good job, and there's a series of works saying why and try to fix that, right? But instead, we are saying you don't try to capture the uncertainty only in the last layer. You want to capture it at all layers.
Okay.
In each layer, the processing is progressively losing information, and at what rate is this happening? For instance, you are distinguishing a cat and a dog. At which layer is it like more confusing than the others, right? And this is a hard problem, and we are finding a way to automatically capture that across the scales.
All right. So another interesting one. What's next on your list?
So another paper that's coming out of another paper that came out of my group at Caltech has been on Sine SGD, which looks at gradient compression. So, right now, when most of the training happens in a centralized way, right? Like if there are devices like IoT devices, they send to the cloud, all the machine learning happens there, and then the data sends back. But you can think in the future, there'll be more of the demand for learning on the edge, especially if you have a lot of video streams. It is becoming impractical to send everything to the cloud. You just don't have enough bandwidth to do that. And so in these settings, in low bandwidth distributed training settings, how do we do good machine learning? And in this case, you need to compress the gradients. So each device does its own pool of data, computes the gradients, but instead of sending it in full precision, in our paper, what we asked was if you only send the sign of the gradient, right? So it appears you're losing a lot of information if you send only the sign. What is the impact? Can we study that? And what we did was to study both from the theoretical perspective as well as the empirical one and bridge this gap. And that's why I'm emphasizing this paper, because we need more that bridge the theory and practice together. On the theoretical side, what we asked was, what is the rate of convergence on the training data compared to the full precision SGD, right? First of all, is it even clear that taking just the sign will converge? Will it go to zero training error? And it turns out, yes, you can get zero training error. And that's because intuitively, when the gradient is large, even just taking the sign means that you're descending in the right direction. Right. And so we, in fact, also argue that there are certain quantities like density of gradients and smoothness and other properties under which we can expect it to have the same rate of convergence as the full precision SGD. And then we went to empirical studies and asked, okay, now can we see that happen? And we saw this converge, very fast. And we also built efficient compression algorithms so that really could increase the throughput and get the gains of compressed gradients. And what we found was on the generalization side, we were getting almost similar accuracies as the full precision SGD, right? And that's why this interface between systems and machine learning is so hard to characterize, because there can be a lot of free lunches. We are compressing gradients, but still maintaining accuracy. And we can also now ask theoretically why, this is the case. And I would love to see more works like this that try to bridge theory and practice and systems and machine learning.
You mentioned building compression. I don't recall if you said compression algorithm or some compression aspect of this. Can you elaborate on that? The sign is easy to get. What do you need to specifically do to kind of support this model?
That's right, Sam. I wasn't talking of a sophisticated compression algorithm.
Okay.
But more the details of, so if you now take the sign, how do you kind of combine across all the parameters and use the right CUDA primitives to make this efficient, right? Like you need to also worry about when in what form you're keeping this and how you're broadcasting it into the system.
Okay. So more the distributed components of it and how everything gets pulled together.
That's right. I mean, the system's details, but it's important to also be about that, right? And many papers stop at either doing the theoretical analysis or like asking what happens to accuracy, but not coming up with efficient implementations that also get the hardware gains.
Okay, great. So what's next?
Yeah, so the next paper is one that's a negative result. So this is coming again from my group at Caltech. And why I want to emphasize it is, it's very hard to publish negative results, right? And people don't want to talk about negative results. And, we tried for a long time to, of course, get a positive result. That wasn't our goal in the beginning to write a negative results paper. And it also took me a lot of convincing my students to say, no, it's okay. You've done a lot of work and this is the honest results. Let's get this out there. And in this case, what we were trying to do was to combine model-based and model-free RL, or reinforcement learning. So, the popular AlphaGo and other examples, what you have is not just the deep Q network, but you also have the Monte Carlo tree search, right? So meaning you have this tree of all possible actions and you're growing this to a large tree depth. In the case of AlphaGo, this tree was of depth in the hundreds. And so, these trees grow exponentially. So you can imagine this is at the end, at the number of leaves is very huge. And this takes a lot of time. More importantly, this requires all these environmental interactions, right? Like you need to ask the environment what happens under each action and keep growing this tree. And in the real world, this would be impossible. Like we could never roll out to such a large tree depth.
Mm-hmm.
And if you're trying to simulate a more realistic real world example, you could possibly do this only for short tree depths, right? Because for the longer ones, there would be too high error propagation. So that's the other motivation to ask what we can do with short tree depths. So when we started out thinking about the paper, our idea was, we will use a GAN-like framework to learn the dynamics and predict it for a few time steps. And then do tree search and DQN combinations and argue that this will give us a good result. That was our initial idea, because then that's a motivation of you can now take this to a more ultimately a realistic example where you can simulate. And instead of interacting with the real environment, you do this in simulation. And we were really worried about the model mismatch between what's being simulated and the real world, right? And those issues. But as we went through it, it turned out to be a very different project. And that's where, I encourage other researchers to also adapt, right? We may go with an original idea, and if that doesn't work out, there may be so many other interesting things you find as you go through the experiments. And in this case, what we found was for the class of Atari games, it was actually quite easy to simulate them. Yes, they are simple images, but we were still surprised in terms of forecasting up to 10 time steps. They did almost perfectly. You couldn't tell the real image from the generated one, visually. You couldn't tell them apart. And that was easy. So we thought the GAN part would be hard, but that was easy. And what was now surprising was even with this perfect simulation, we were not able to get good results. So in fact, I'll take it back. In the first game, the Pong, which is a simple game, we got really good results. We got, we showed that with just half the number of samples, you could beat the baseline DQN or the DDQN network. And so that's promising. Now we're okay, we'll scale up to more games and we will write the paper, right? But as we started, and so as we started, doing these experiments, and it was performing worse than DDQN. It was performing worse than random policy. And we are like, okay, what's going on? Like, is there a bug? I mean, like, what else can we do? There's so many tweaks the students did. And, Kamyar and Brandon, who were mainly doing the experiments, and still it did not work out. And so then we took a step back and asked, okay, why is this the case? So it turns out that if you're using these short tree depths with your TQN model, it can be worse because you're not getting the negative experiences very well, right? So think of it, the analogy I would give is like a helicopter parent, like, not getting these kids to make mistakes, always like hovering around the kids. Right, hovering above the kids and making sure they are okay and like kind of protecting them. So these short tree depth Monte Carlo tree search is doing the same. Let's say this agent is near a fire where, if you went into the fire, you'd get killed, you'd get a very large negative reward. And that would happen with the DQN because there is no protection, but it would learn, okay, I should avoid the fire because I'll get killed. Mm-hmm. But if you have this Monte Carlo tree search, it'll look out a little bit into the future and realize, oh no, I shouldn't go to the fire because I will get killed, so I will avoid the fire, right? So it takes a long time just avoiding the fire, never getting killed, but not making good progress either. And that's why you need large tree depths, because then you have a global view, right? And now then you can do really good decisions. But having this myopic short tree depth actually hurts you more than helps you.
Are you planning to extend this based on the success that you had with the prediction part?
Yeah, so I mean, certainly on the simulation side, how we can simulate the dynamics in different applications, even real applications involving control systems that we are very interested in. And also, now the question is, how can we fix this, right? If it's not this classical Monte Carlo tree search with DQN, what are other reinforcement learning algorithms that could help us combine the model based with the model-free reinforcement learning?
Cool. So I think you had like 7 papers. We've got through 4 of them. What else have you found interesting this year?
Yes. The other 2 are more, I would say, the applications of AI to the sciences.
Okay.
This has to be the future, right? We need to go and impact the scientific questions, the very fundamental discoveries. I think that's really important. And I'm happy to see 2 papers that I think have been great. One of them is called the phase link. It's a deep learning approach to seismic phase association. And this is from my colleague, Isong Yu at Caltech, who is also a machine learning professor, and other seismic researchers at Caltech. And here the goal was to ask, can we link the unknown phases from different sensors for a common earthquake? Apparently, like, these phases are not known, and this is something you need to do when you have so many different sensors that are trying to sense the same common earthquake. And in this case, it's challenging because you don't know how many sources, like, is it just one earthquake shudder or is it happening in different places? And these events could be happening frequently in time. So it's not just one shudder, but multiple ones, and there's overlap. And how do we disentangle all this well, right? And the challenge here was that there is little real data, right? So, I mean, I think at Caltech, we have the longest recordings of seismic activities, at least in the United States. Goes back almost a century. But this is still not enough if you want to come up with a very good model, and especially for deep learning, which is data hungry. So instead, what the researchers did was a simple and an effective approach where they simulated synthetic sequences. So there's something known as the P wave and the S wave. These are different kind of waves in earthquakes. And so they simulated both these kinds. The arrival times were generated using just a very simple one-dimensional velocity model. So no, this was nothing complicated. We're always, when we are generating synthetic data, we're worried, is this realistic enough? But what was surprising in this case was this simple synthetic model, when tens of millions sequences were used, combined with real data, was very effective. And to me, the intuition is this is encoding all the physics of the waves in an effective way, right? So the basic physics is encoded well. And then with some amount of real data, any additional variations, it's able to also capture. And, so to me, this is a good example of going into a different field, understanding the problems in that domain well through the domain experts, and coming up with the fairly simple machine learning solutions, but that have a big practical impact.
I've certainly seen in my conversations with folks on the applied side that they can accomplish a lot with some fairly basic tools that the ML and AI have provided. So with deep learning, there are tons of applications that can dramatically simplify some of their previous workflows as researchers that aren't particularly complex, that are fairly off-the-shelf applications of for example, image classification or deep learning classifiers or predictors.
So I agree to the extent that the machine learning principle is simple, but at the same time, this required close collaboration between the machine learning expert and the domain experts, right? Like, it's not a plug and play approach yet, and I believe in most applications it won't be, right? And just taking the standard deep learning, you usually don't have enough data, and you have to see how to augment the data or how you should do semi-supervised learning well, and that's why this is usually requires close collaboration and not just the domain experts using some off-the-shelf machine learning tools.
Yeah, that's fair. And I think that, there's often the challenges come up in the data side, getting enough labeled data, or coming up with tricks to improve sample efficiency. Or I've also talk to folks that have to kind of customize their objective functions to do interesting things. But it's not like they're using, exotic things like Gans very often at this point.
That's right. And I would always suggest people to start with the simplest things. I was in this mentoring session for reinforcement learning. The topic was reinforcement learning. And there were many people coming from the applied side and asking when they should use reinforcement learning. And my answer was only when someone puts a gun to your head. I mean, if you run out of everything else and there is nothing else that works, then try reinforcement learning. Because reinforcement learning is expensive, right? So first, you want to ask, how much of knowledge do I already have? What kind of pre-trained models are effective? And, do I really need to explore here, or do I have enough data to begin with? I mean, these are all things you want to think about rather than blindly applying reinforcement learning.
And you mentioned the next paper on your list is kind of in a similar vein, an application on the science side?
That's right. And also on the system side. So this is the paper on exascale deep learning for climate analytics. And this won the Gordon Bell Prize this year at the Supercomputing Conference. And to me, this is very exciting because for the first time, this broke the ExaOps barrier, right? So to me, it's mind-boggling the scale of computations we're able to do now. This had the scaling up to 27,000 GPUs, and this is on the new Summit supercomputer. And traditionally, supercomputing has been very CPU-based, and now taking this to the next level with GPUs is very exciting. And the other question is now, what kinds of applications can we do on the supercomputing? Traditionally, it has been HPC, kind of climate modeling. So there are these known climate models, and how do we simulate this, right? But in this case, the unique thing was to combine those HPC models with deep learning architectures. Specifically, they applied segmentation architectures to climate data sets, and they achieved state-of-the-art weather pattern masks. And they had both the FP16 cores and the traditional HPC operations, right? So this kind of mixed precision and mixed operations of both HPC and deep learning together, I think, will be the future in the sciences.
Yeah, it's interesting. It's my understanding from conversations that for quite a long time, maybe I don't know if it's machine learning or GPU-based architectures weren't really appreciated in the supercomputing community. And for example, I think the anecdote that I heard was that was really the reason why Jensen and NVIDIA created GTC, because they couldn't, the researchers that were working on GPUs couldn't get any papers accepted at supercomputing.
That community is hard to break into. There are so many I can go into the sociological factors, right? And that's because, they are in the big labs, the big national labs, and the people who've trained on those traditional supercomputing for decades, and they don't want to move away. So I still see these issues, but this is where we need, especially the younger people, to say, okay, no, there is so many new developments that this is inevitable, right? We have to move away from those traditional supercomputing. And same with machine learning. They, demanded these high precision operations, 64-bit operations, right? And that's no, in machine learning, everything is 32 bits or lower. And that's because in machine learning, the idea is what we are computing anyway is inherently uncertain, and we don't need high precision. Whereas in traditional HPC, the idea is we'll precisely maintain the uncertainty quantification. And in some cases, this is super important, right? There are certainly cases where this is needed. But in many others, the model itself they're using has a big mismatch, right? If you're using a linear model and you want this high precision, you could argue, is this really needed? And so what I believe is we should revisit and ask, when do we need these very high precision computations? And are there other parts of the pipeline where we could relax that?
So maybe let's switch gears a little bit and talk a little bit about your predictions for 2019 and more broadly the near future in machine learning and AI. And in particular, I want to start with, what are you most excited about when you kind of think about where we are today, all that, we've accomplished in 2018, the struggles of 2018 that you're intimately familiar with. What are you most excited about going forward or looking forward?
Yeah, I think 2019 will be a great year for really expanding the horizons and the way we think of machine learning, right? I think there'll be hopefully less of leaderboard chasing and myopic gains in deep learning, and more. Now I'm serious, and more of a holistic approach and integration with the other sciences, with the humanities in a stronger way. Going beyond standard supervised learning. We know very well that the scenarios where the trained machine learning models are used will differ so much from the training data. Can we come up with new frameworks to detect these domain shifts, especially in safety critical applications? Can we come up with ways to learn online, as we are getting this new non-stationary data, right? Can we do lifelong learning and never-ending learning and keep getting new knowledge? And when we go to these new domains, can we infuse that domain knowledge? For instance, can we ask what is the knowledge of physics we can already build in, if especially we want to do learning on our robots or drones? There's so much that's already the control people have developed, right? We can't throw all that away. There is no way. Instead, the question of, do we bring in learning in a principled way? Because for control systems, for instance, you want stability. You cannot throw that away, right? Whereas neural networks by themselves are not stable. How do we enable that? And we had some initial work this year on enabling a stable landing of drones with stability guarantees. So those kinds of collaborations across different expertise and different groups, that's what I hope to see more in 2019.
I'm curious, you mentioned one of the papers that you highlighted was reinforcement learning, and of course your comment about it being a tool of last resort. Do you expect to see that change much in 2019? How close do you think we are to the point where RL becomes a useful kind of general purpose tool for folks not in the research community?
I like that, Sam, how you put me at a spot, because yes, I work in reinforcement learning. To clarify, I have a great student on the market, Kamyar Azizadeh, who has done amazing reinforcement learning work. And we certainly should do the principled approaches, ask what would reinforcement learning do in different scenarios, what are the algorithms, and how can we analyze them. And when it comes to the practical setting, my comment was, don't blindly apply, right? Is it what you need here? Is it reinforcement learning? And to me, some of the most interesting work will be in the robotics side. So I talked about my Caltech project for landing of drones and autonomous flying of drones. So this is where we need the domain experts, but we also need precise measurements. So in this case, in the CAST facility there, we have a unique wind testing facility for drones where we have 1,300 programmable fans that can generate all kinds of wind conditions, and we can get precise data on how the drone would react. Right. So now, armed with this data, we can ask what kinds of reinforcement learning and machine learning we can do very well. Because without this, there is no hope of trying to improve these systems. And so data collection is important. And when you have less of this real data, that's when we need very physically precise simulations. And this is where at NVIDIA, I believe we have this unique capabilities to do simulations extremely well. So there are two frameworks. There is Flex and PhysX. PhysX is a framework. We made it open source recently, earlier this week, here at NeurIPS, which is simulating real-world physical behavior very precisely. Right, like think about how if you have a damage to a building or you have like movement of the cloth, how do we make them realistic? And Flex is a system that is also high fidelity GPU based physics simulator, and it simulates these rigid body dynamics very well. And Dieter Fox at NVIDIA and his group has been using Flex very effectively to close the gap from simulation to real. So the main idea is you may not even know what to simulate in the simulations, right? You need the real world experience rather than trying to manually tune what to simulate. What they're doing now is doing a little bit of a real world rollout, and based on that experience, learning what to simulate next. And so going back and forth between simulation and reality. And I believe in 2019, we'll see a lot more of such sim to real applications, and that'll lead to more realistic robotic impact, more realistic impact in robotics.
Do you have some specific predictions for kind of what you expect to see in your area and in ML more broadly in the next year or so?
So the main one is moving beyond just supervised learning, right?
Okay.
So semi-supervised learning, asking what are the relevant generative modeling? How do I capture uncertainty in a relevant way? The Bayesian neural networks, how do I design them in the right way? And through that, how do I do better active learning? How do I do domain adaptation better? How do I scale up the algorithms while understanding these trade-offs between systems and machine learning? I think we'll see a lot more of those kind of interdisciplinary questions as well as the core machine learning questions.
So any parting thoughts before we finish up?
No, I think I should say like 2018 has been personally a challenging year because, I have had, I think, the time to introspect more on the societal impacts of machine learning and how we can improve diversity and inclusion in machine learning. I think the year is now ending in a good note, especially at NeurIPS, as I'm seeing so much overwhelming support. And hopefully we can improve that. And with that, come up with new creative approaches to machine learning. Hopefully less of the media hype, more of serious podcasts such as what I'm doing right now. And I've been very vocal in dispelling some of the hype and the myths, and I hope to continue to do that.
Fantastic. Well, Anima, thank you so much for all of your work in the space and for taking the time to chat with us about it.
Thanks a lot, Sam. This is a pleasure.
All right, everyone, that's our show for today. For more information on Anima or any of the topics covered in this episode, visit twimlai.com/talk/215. You can also follow along with our AI Rewind 2018 series at twimlai.com/rewind18. As always, thanks so much for listening and catch you next time. Happy holidays.